think the recorder is just about to start.
Just have your phone remind you 50 minutes into the class.
Yeah, well, you guys did a pretty good job in app programming to remind me of that. All right, the recorder is on, so I'm going to get started. So I usually start with homework assignment due on the day. I usually start with the homework assignment, and then I'll move forward to new material. So in this case, let's go ahead and talk about at least the first one. The second one, I don't know. I mean, I did it in class, once already, so I don't think there's really not much. There's really not much to do about that one. But this one, I can go ahead and show you how to do it. So the key is I want you to design logic gates to implement this particular expression. And I did not ask anyone to simplify first, so I'm hoping nobody actually simplify it and make it so that it's just A and B, which is basically what it is. But if you do, I don't really mind that much, because it shows that you know how to simplify Boolean expressions, so it will be okay too. All right. So the first thing we have to do is to look at this expression and figure out how the operators are structured. Okay, that's the first thing we have to do. This is something that is not, that I have not really taught in this class, but for the most part, you know how to read expressions like a regular, addition, subtraction, multiplication expression, and you know how it is structured too. For instance, if I just give you something like this, okay, 5 times -4 plus 5. Now I know you can evaluate and find out the answer right away, but if I ask you how, which operator is applied to which value, you probably can tell me exactly, what the order should look like. Multiplication is the last one, okay, because it is appearing, it's on the 5 on the left. It has 5 on the left-hand side, and then it has this whole thing in parentheses on the right-hand side. So I can't really do the multiplication until I know what is the result of whatever is inside the parentheses. The addition is inside the parentheses, and the addition also takes 2 values. One value, the one to the left-hand side, is a -4, and the one to the right-hand side is a 5. So are there any questions about looking at an expression and figuring out how it is structured? Now I chose this particular expression for a reason. Do you think? Yes, go ahead.
Are logical operators distributable?
Yes, it is. So you can distribute it if you want to, but the question did not really ask you to do anything to simplify or to distribute the operator. So in this case, I chose this particular structure because the 5 is really taking the place of A. This 4 is also A, and this is B. Is that making any sense? Okay. All right. So the next thing we have to do is to figure out, okay, but how do we turn this into a gate representation? Okay. So when you look at the gate, last time we looked at a few. When you look at an AND gate like this one, which side is the input and which side is the output?
Left side's input.
Yep, this side is the input and this side is the output. Okay, so same with the OR gate, like that. And if you want to, you can also use a NOT gate, which is a triangle with a bubble. Okay. Now, how do I know this is an AND gate and this is an OR gate and this is a NOT gate?
They have the same shape all the time.
No, but
without knowing the shape.
yes. If I just use logic sim, how do I know that this is an AND gate, this is an OR gate, and this is a NOT gate?
You could, I was about to say, you could test it. You could put out 3 pins, and then since you know the truth tree, you probably should.
Well, let's find out, okay? Because in logic sim, this is actually, well, I wouldn't call it spelled out, but it's actually there.
That's how you run that thing.
All right, so this is logic sim. So the first thing we know is, we have to rely on some gates, right? And if you just look at the toolbar, what do you see on the toolbar?
Inputs, outputs, the gates.
Yep, the input pin, output pin, and 3 most common gates. And what are those 3 most common gates? Well, let's find out. Okay, if you hover, okay, it doesn't say. But if you go to gates here, you can see that this is a NOT gate, this is an AND gate, and this is an OR gate. So that's how we can find out. Okay, oh, so that is what gate, that is what other gate, and so on and so forth. Is that okay so far? Okay. All right. So now that we know this is the structure, if you want to turn it into a gate diagram, what you need to do is to kind of tilt your head like this, and it becomes a schematic. Okay, with gates. So instead of a minus here, we have a negation. So a negation is a triangle with a bubble. Instead of an OR, we have instead of an addition, we have an OR gate. So an OR gate looks like this. This is the input, that's the output. And instead of a multiplication, we have an AND gate or conjunction gate, which looks like this. And this is my output. Yep.
Is the bottom A mislabeled?
This one is, they go to the same pin. So, A is a pin, and these two go to the same pin, and B has its own pin.
You had it 5 and 4, saying that they're the same.
Oh, yeah, well, I actually corrected and say this is actually our A, and this is our B. The place is the same, although the constants do not correspond to the A's and the B's. Right, so let's go ahead and draw this out, and then we'll go ahead and simulate it. And so we'll start with a NOT gate, put it here. Let's magnify a little bit so we can all see. So here's my NOT gate. The output of the NOT gate goes to a OR gate. Okay, so let me leave some space for the AND gate. So we need an OR gate here. All right, this OR gate looks a little bit bigger and has more input than we need. So we need to change the number of inputs. Instead of 5, we just need 2. I personally do not yet. Go ahead.
So if you don't change the input to 2, if you just leave it 5, is that a problem?
I don't know whether it can simulate without changing the number of pins. Would it still simulate correctly?
No, I think there'd be a problem because you're having an issue with.
Because it's not determined, right? If the input is not determined, you cannot simulate it. Okay, so you have to change the number of input pins to 2 in order to get the simulator to work. We'll change the gate size to narrow. I just like to use a smaller gate like this one. So we'll put it here is good. And then we need an AND gate, so we'll put an AND gate here. Same thing, this one has way too many input pins. We'll change it to 2 also, and then change the shape to narrow. Now, if you don't change the shape of the gate, it's not a big deal. Okay, if you leave it as the big one, it's not a big deal. As long as the connections are done correctly, it will still be okay. All right, so, and we need 3 pins. We need 2 input pins and 1 output pin. So for the input pin, I will put one right about here. And it doesn't have to look good, it just has to be functional. So I'll put one here, and the output pin is going to be on the side. Now, because this one is going to be the output pin, I have to specify output to be yes, and it is better to make it face west, just so that the connection point is right next to the connection point of the AND gate. And now all that is left for me to do is to make the actual connections.
1 input.
Sorry?
You said 3 inputs.
3 inputs? Oh, okay. I misspoke. 2 inputs and 1 output. So together, 3 pins altogether. And this one hooks up to the same one here. This one hooks up here. This one hooks up here.
That's might be what the issue is.
And this one hooks up here. And this one hooks up here. So the gates are now all connected. And if I want to, label it, I just go here and label this one to be my pin A, or input A. This is my input B, and this is my output. And now we have the schematic all done. It's nicer to put the text of output to the other side, but this is fine. I can read it so that it's not a problem. So are there any questions about the construction of the schematic itself?
Instead of using a NOT gate, could we just negate one of the?
Yes, you can. Yep. So if you want to save a NOT gate, you can use the negation of an input pin of the NOR gate, and so the bubble will appear at the input, but the top input pin over here, and it will still do the same thing of negating that particular input. So that works as well. Not a problem. All right. So it's time to do the simulation now, because I want you to tell me how to make the output pin a 1, how to return on the output pin. So now we can do the simulation, and we can turn one into 0, turn the other one also into 0. The output is not a 1. Turn pin A into a 1, the output is still a 0. Turn pin B into a 1. Okay, so that's one configuration that can give me a output of a 1. But let's double check the last one. Turn this off, and the output becomes a 0. So this is the only configuration that can give me a 1 at the output. And that's the other part of the question, is how do we turn on the output? That's it, both answers, the schematic, and you have to write in the comments, how to turn on the output. I kind of skimmed through the answers, right before class, and I would say the majority of the class, got it. They commented and they explained all the things. Yep. You can put a truth table too. If you put a truth table, and in the truth table it shows that the output is on or becomes a 1, only if A and B are both 1s, it will serve the same purpose. Yep. All right. Are there any other questions? Other questions? How long did you guys spend to get this one done?
Too long.
About an hour. Okay. Well, within that hour, you spend some time to get used to the tool as well. And that is not time wasted, because we are going to have some fun with Logic Sim. It's just a very useful tool to explain the inner workings of a processor as well as memory. All right.
Can you explain the diagram in reverse order, because it confused me when we join the not A with the A?
Because they are both A's, so they just connect to the same point.
Okay, so we're going. Okay, because I see it as. All right, I see what you're saying, but it just seems weird in reverse order.
It's the same variable basically. All right. So with this out of the way, and with a second introduction to use Logic Sim, as at this point, we'll continue to talk about a half adder, and then we'll talk about a full adder, and then we'll talk about how do you make a general purpose n-bit adder out of half adders and full adders, kind of daisy chained together. Okay. Which turns out to be your homework assignment as well. So.
So convenient.
It is very convenient. For the other homework, I'm not going to show you guys, because I did it already. If you just watch the video and kind of replicate all the steps, you'll get the second one done. Yep.
I mean, that data it gives me a wrong output.
Sorry?
It gives me a wrong output.
I cannot see it right now, so I can't really comment on your particular design at this point. All right, so this is what we're gonna do today. In the lecture, what I'll do is I will finish up addition and subtraction in binary. We'll talk about half adding and full adding, and in that discussion, the answer or the solution to your homework assignment is going to be pretty clear. Okay, and you can just you just have to put some time to put something together. The challenge of this particular homework assignment is to design your gates hierarchically. So you have to kind of design something, test it. If it does work, package it. Okay, make a new component out of it, and then you put it into your library, and then you can make more instances out of it. I briefly demonstrated that particular ability in the previous class. Okay, so you basically package things together. And then in the lab time today, I have some demonstration how to use GDB as a debugger. We haven't really talked about assembly language programming yet, so I'm not going to show how to debug an assembly program because it doesn't make any sense. But since all of you know C or C++, we'll start with some interesting buggy program written in C, not C++, just regular C, no classes, no objects, no constructor or destructor. Those things, can be also kind of complicated and do weird stuff, on their own. But this is just regular C. I can even give you a preview of what these programs will look like. This is the first program. Okay, the entire purpose of this program, some of you probably recognize a little bit of this code, is to reverse the order of characters of something that you type on the keyboard. Okay, so the program will prompt you to type something. You type something in, and then the program will reverse, the entire string and print it back out. Okay, that's the entire purpose of this program. But it behaves in a weird way. Okay, the program does crash under certain cases. Okay, so what I want to do is to show you how to use GDB to figure out why the program is crashing. Okay, the second program is even more fun. I really like this one. This is kind of like a trademark program that I use to introduce the rationale of understanding assembly language programming in this class. Because most people look at assembly language programming and say, I just want to write games. Why do I need to know how to write programs in assembly? Come on, just let me graduate already with a good GPA. Well, the thing is, if you write programs in C or C++, the two most dangerous high-level programming languages, inevitably, somebody will at some point run into this particular problem. Now this one, I made it very spelled out, okay? But even so, people know that this is not right, and they don't know what would happen when this program runs. Okay? Most of you look at this program, first of all, it looks pretty harmless, doesn't it? Okay? Okay, some of you already identified if F is not really that harmless, because the local variable x, which is an array, has 16 characters. But when you write an array in C, the index of the first element is 0. Okay? So when you have 16 characters in an array, what is the index of the last character? 15, right? So what is x bracket 16 then? It's not a part of the array. Or maybe it will, like VB, it will complain and say, index out of bound, the program will just, doesn't crash, it just gives you an exception. There'll be a little dialog box on the screen saying, okay, on a certain line, there's an index out of bound issue, and it stops the program. No, C will just kind of silently do something that is not supposed to. Okay? But the big question is, what is the symptom of this particular program? We know it's going to do something bad, but what exactly is it going to do? Okay, so in today's lab session, I'm going to run this program, and you might be, I wouldn't say surprised, but you might find it amusing what this program is going to do. Okay, it does get back to main without any issue, but when it does get back to main, it will do things that you go like, why would it do that? Okay, so I'm going to demonstrate, how you can use a debugger to at least figure out that something is wrong and potentially what is causing that problem. Okay, at least you'll be able to locate the problem, even though you may not understand why this problem is causing that particular symptom. But you at least know that symptom or the cause of the problem is here, which is important. Okay. Are there any questions about this particular program? We'll see that again in the lab time, in the lab session. But at this point, I'm just going to show it to you because it doesn't look very interesting. Okay, it looks like, it looks kind of boring, right? I do some assignment to some variables. I declare an array in the subroutine that I call. I change one of the elements, quote unquote, one of the elements, and then I return from the subroutine without doing anything else. And then I print the values of 2 of the 3 variables that belongs to main, and I return 0. I mean, it doesn't seem like anything really bad is going to happen, or anything too mysterious is going to happen. Maybe the program will just crash at some point, okay? Which it does, but before it crashes, it will do something that is totally weird to at least most of you. Okay, so I'm going to leave it up to the lab session to talk about this one. But the main purpose of the lab session today is really to go through GDB to show you guys the commands that you can use in GDB to debug a program, how to stop a program, how to examine memory locations, and so on and so forth. Okay, which will be useful in assembly language programming. All right. So with that out of the way, we're going to start with binary number addition and subtraction. We have kind of talked about this already. We talked about addition, and then we also talked about, this is a multi-digit addition, by the way. It goes through the sequence step by step. It shows you how we are adding two binary numbers. So let's go ahead and just do this, okay? I'm going to do the same exact example today in class as in the notes. So this way, if you have any questions, you can refer back to the notes to find out, oh, okay, but what happens when we add those two numbers together? All right. So the way I do this is not really exactly the same way that you learn how to write out addition in school, because I use one entire row to represent the carry bit from previous digit. And let me identify which row I'm talking about here. I'm using this row to represent the carry bit from the less significant digit. Okay? Because usually it is not represented like this, but I would like to do it this way because then it becomes kind of clear why the name of half adder is called, the mechanism that we'll talk about next is called a half adder. Okay? And why do I stick a 0 there already? The 0 is not even calculated from anywhere. Why do we stick a 0 over there? It is already the least significant bit. Okay, if it is already the least significant bit, then it's not going to get a carry from somebody else's addition. So that's why it's a 0 over there. Is that okay? All right. Okay, so let's go ahead and do this computation here. I'm going to use the mouse cursor, not the mouse cursor, but the text cursor, kind of like my finger. So this way, I can kind of show you where to direct your attention. So we are first going to be adding this one to this one. If you still remember from last week's discussion, what is 1 plus 1?
0.
0 with a carry. With a carry of 1. Very good. Okay. So we'll put this result of 1 over here. Oops. And it has a carry of 1 to the next digit. Are there any questions about how I wrote the carry from that 1 plus 1?
Shouldn't it be
1
0?
plus 1 should be 0, right? What?
1 plus 1 should be 0.
Oh,
carry
you're
one.
right. Yep, 1 plus 1 is a 0 here. Excuse me. So that one's supposed to be a 0. Thank you. So 1 plus 1 is 0 with a carry of 1. Now we have another addition. 0 plus 0 is 0. And this time it does not have a carry of 1. Are we doing okay so far with the first column? Now we move on. We move on to the second column. 1 plus 1 is a 0 with 1 with a carry of 1. 0 plus 1 is a 1. Now we move on to this one. 1 plus 0 is a 1 with no carry or a carry of 0 at this point. 1 plus 1 is a 0 with a carry of 1. Now, it's kind of important here because you can see the carry of 1 to the next digit can come from the first addition, which is the top two row, or it can come from the second addition, which comes from the third and the fourth row. So either addition of a column can contribute a carry of 1 to the next digit. Is that working out okay so far? We have a similar scenario in base 10 addition too. Because the carry that you're adding to the next digit can trigger a carry as well. Yep.
So if there was already a 1 there, what would you think? How would we indicate? So if that would have been a 0, if we would have had to add another, if there was already a 1 where you just placed it, what would we do in that situation?
Only one of them can contribute.
Okay.
Only up to 1 can contribute a carry of 1.
Yeah.
So you cannot end up with a scenario where both addition will contribute a carry of 1.
Okay.
Now, there are scenarios where neither will contribute a carry of 1. So that ends up to be a carry of 0 to the next digit. That's a good question. I think we might have a case like that here too. All right, so we have 0 plus 1, which is a 1 with a carry of 0. So I don't write a carry of 0 because there's a chance that it might turn into a 1. And then we have a 1 plus 1, which is a 0 with a carry of 1. Now this time we have 0 plus 0, that's an easy one. It has a result of 0 with a carry of 0. 0 plus 1 is 1 with a carry of 0. So in this particular case, we have nobody is contributing a carry of 1 from both additions. So that means the carry to the next digit is going to be just a 0 because nobody contributed. Okay. So we have 1 plus 0, which is a 1, and with a carry of 0. 1 plus 0 is a 1 with a carry of 0. Once again, both additions end up with a carry of 0, so that means this is going to be a 0 here. 0 plus 1 is a 1. 1 plus 0 with a 1 and a carry of 0. 1 plus 0 is a 1 with a carry of 0. So once again, we have a 0 here. And then 0 plus 0 is a 0. 0 plus 0 is a 0. And that's my conclusion. Let's double check and make sure that this addition, I did not screw up anything in this particular exercise. So what we'll do is we'll convert everything into base 10 and then carry out the base 10 addition. All right, so this one is 1 plus 2 plus 4, no 8, no 16, 132. This one is 1 plus 2, no 4, 1, 8, and then 1, no 16, no 164. Okay, so that becomes 39, and that becomes 75, and let's do this part here. This is 2 plus no 4, no 8. There's a 16, there's a 32, there's a 64.
I think it's 114.
114.
114? Okay, thank you. All right, so do they match?
Yes.
Yep, they match up. So if I did make a mistake, I cannot make a single mistake. I have to make some number of mistakes that turn out to cancel out each other in order for the end result to look like this. Because the base 10 addition works out awesome. Yep.
Is there any theory or work that's done on that second half add, like what those numbers turn out to be, or what the carries would turn out to be? Like, is there any?
No, none that I know of. Okay, none that I know of. And I'm the only person who write out the carries on its own in its own row as well. Most people don't do that. Most people just use a little 1 or a 0. Yep. But this is important because this is really important because it really shows you, in one addition operation, like this number plus this number, it really has two results. It has one result that goes here, and it has a result that kind of goes there, okay? Not entirely, but kind of. And then we have another addition in the same column, which is this number plus this number, and then the result goes here, and then the carry also goes here. Is that okay so far? Okay. And what we want to do is to figure out, how do we express everything in logic gates, okay? Because that was the essence of last week's lecture. Was, on one side we have numbers, values, representation of quantities, base 2, base 10 numbers on one side. On the other side we have transistors, we have NAND gates, and then we turn those NAND gates into NOR gates, OR gates, AND gates, and negation. But there's no connection between the two until we get to this part here, because the rules of binary addition can be implemented using logic gates. Do you guys kind of vaguely remember the rules of addition and how that translates into logic gates?
Yeah.
Okay, so we'll just go ahead and mention this here. All right, so I'll just go ahead and do a 2-bit by 2-bit addition here. So we have AB plus CD here, okay? And the results will be indicated by other, digits. So we have EF, and then the carries will be G, and then this one is always a 0, so I'm not going to use another digit to represent it. And then the end result here, G, H, I, J. Okay, I'll just use H and J and skip I, because I looks way too much like a 1, so it's, I just want to avoid any potential confusion here. Okay, so in this particular case, A is just a bit, okay, it can be 0, it can be 1. B is a bit, which can be a 0 or 1. C is the same way, D is the same way, okay? So the input into this 2-bit by 2-bit adder will be 4 individual bits, okay? 2 bits, which is the first number, AB, 2 bits being the digits of the second number, CD. The intermediate bits, E, F, G, and 0, they're not really that important because I really just want to get to the sum, which is H and J. Okay. I will also make a K here. Okay, K is kind of like a leftover carry, which is actually of significance. So I'll keep K, on the side here. All right. So let me just make it clear. A, B, C, D are input bits. H, J is the sum, and K is the leftover carry. Because it is a carry bit that doesn't really go anywhere. It is not really represented as a part of the result, but yet in a processor, it is remembered. Okay, we remember the leftover carry of an addition. All right. Yep.
A, B, C, D, these letters, just a symbol or it's
They are variables. Each one is a bit. A is a bit, B is a bit, and so on.
Is that same as 0, 1?
Huh? It can be a 0, it can be a 1. It is a variable that can be a 0 or 1.
So we didn't use it for asking of the code and do some calculating there actually.
Sorry?
Did we do some calculating?
No, A, B, C, D are not calculated. They are inputs. They are independent input bits.
But A, B is 1.
AB represents a number, okay? Because AB is basically 2 independent bits. So, AB together is representing a 2-bit number, which can be 0, 0, 0, 1, 1, 0, or 1, 1. Same thing with CD, it is just representing another binary number, which can be 0, 0, 0, 1, 1, 0, or 1, 1.
How about A, B, C? Is that 3? If I use A, B, C, is that 3 bits?
No, because in the way I organize this is AB is one number, CD is another number. Because a 1-bit by 1-bit addition is not that much fun, and a 2-bit by 2-bit is a little bit more fun. Okay. All right. So what we want to do is to figure out, the logic expressions, so that we can figure out what is F. Okay. Let's start with F here. F is the result of B plus D. Okay. But do you remember from last week's discussion, what is the logic gate expression, or the logic expression to get F from bit B and bit D?
Isn't it a NAND gate?
This is what is the result of that condition.
It is exclusive OR.
Yeah.
Yep. Okay. So you can either use exclusive OR, or you can use the long form of exclusive OR using negation and disjunction and then conjunctions. So we'll just use exclusive OR. Fine. Okay. Fine. So. Okay.
Just for that.
So F is B exclusive OR D. Now this is an important step because what we're doing now is we're translating arithmetic operation that has to do with numbers, values, quantities, and whatnot into logic operations, which is all involving just true, false, zeros and ones, high voltage, low voltage, transistor on, transistor off. Okay? So we're translating from values, numbers that we want to represent to physical quantities that the computer can actually handle. So this is actually a very important step. All right, so if F is that, 0 is just 0, so we can just say that J is the same as F, right? Because anything plus 0 is just that anything. So I really did not need to use J. I could have just write F, in place of J. But, that's okay too. Not a problem. All right. Next, we have to also specify G, right? What exactly is G?
G is
Just from this
Carry.
location, it is the carry of. Now, this one is tricky because this carry has two possible contributors, right? Because B plus D can contribute a carry of 1 to G. Well, I guess F plus 0 cannot. So in this case, it's not, cannot be or. So in this case, it's easy because only B plus D can contribute a carry of 1. Okay, so that's an easier equation. And what is that equation? E and D. Okay. All right. And how about E?
E is the results of the exclusive OR AC.
Yep, exclusive OR, the exclusive OR of A and C. Okay, very good. We know what G is already, so let's try to figure out H first. H is the easy one. H is
H is
X
the
or G.
result. E and G and? No, exclusive OR E and G.
E and G, right? E exclusive OR G. There we go. Because it is the result of adding bit E to bit G. Is that okay? What about K? K is the first time we see a carry bit that can have two possible contributors. Because A plus C can contribute a carry of 1 to K. E plus G can also have a carry of 1 and contribute that to K. So
would it be
So it's going to be the and of.
and the or?
okay, let's figure out the components first. Okay, so I'm going to do this. I will basically give you the two components, and then we'll figure out what has to go here to kind of combine the two components. We know what the first component is, A and C, right?
Yeah.
Because if A is 1, C is 1, then they will contribute a carry of 1 to K already. Not a problem. On the other hand, if E is 1 and G is 1, they will also contribute a carry of 1 to K. So we have E and G over here. Are we doing okay so far as the two components of K is concerned? The big question is, what do I use in place of the question mark? Because I have two components, I need a way to combine the components. Or is the correct answer.
Oh, or. So
Just a regular or. Yep.
How do you draw exclusive or like what's the symbol for that?
The symbol of exclusive OR is a plus with a circle around it. Sure. Okay, here's a quick quiz. In C, as a bitwise operator, how do you specify exclusive OR?
The carrot.
A caret, that's right. So in C, it is a caret, which most people think is to the power of, which obviously does not work out. Cool. Okay, so now that I have the equation like this, would it be difficult to add, two more bits here? Would it be difficult for me to add another bit here so that the first number becomes a 3-bit number, add another bit here so the second number is also a 3-bit number, and extend it so that this now becomes the leftover carry? Would that be difficult, or would it just be kind of like, oh man, we just need to follow the same format and just stamp out another, bunch of bits? Same way, right? I mean, the principle is basically the same thing. Okay. So at this point, I want to indicate what makes a half adder. Okay, a half adder is doing this part here. This is a part of a half adder. This is the other part of the same half adder. In other words, when you look at a half adder, it has two input bits, okay, because we are adding one bit to another bit. It has two outputs. One output is the actual sum, okay, the result, and the other output is a carry that will be used later on to calculate the carry of the next digit.
Wait, hold that. Brain fart real quick. Could you repeat that?
Sure. A half adder has two inputs. Okay, so we have in1 and in2 as the inputs, because we are adding 2 bits together. So these two represents they represent the bits to be added. It has a result, which is the sum, and it has a carry, which eventually will be used to calculate the actual carry to the next digit.
And we can look at C and R as those are outputs of whatever operation we perform
Correct.
on the first.
So
digit.
this is the output, this is the output, these two are inputs. I'm using the notation of
Yeah.
logic sim.
Okay. So we just have, we did it, we built it.
Yep.
Just an exclusive OR gate and
Yep.
AND gate.
So if I were to ask you to write out the actual gate configuration inside an HA, would you know how to do that? And you know, for this class, I'm going to give you guys a break. You can use the exclusive OR gate. I mean, if you cannot use the exclusive OR gate, you know, you just have to kind of break it out into two AND gates and one OR gate. That's basically it. Okay. But that is only one half of a adder. That's why it's called a half adder. Okay? Because it is only responsible in this case, you know, adding B and D together has its own result, which we call F, and it contributes, you know, to the carry bit G in this case. Now, because F plus 0 cannot contribute a carry of 1, so we don't have an issue. But when you look at the second column, or the most significant bit, which is A plus C, then we have two ways to contribute to K. A plus C, okay, will have an output of E here, and it will contribute a possibility to K. And then what we do is we take E, and then we take G here, and this becomes H, and this becomes a part of K as well. Okay? So when you look at the picture, okay, keep your eye on that picture, and I'm going to redraw this one. Okay? And use exactly the same label. We have bit A and bit C, okay, in the second column. It has one result, which you can go to either one because it's symmetric. So the result of this half adder becomes what we know of as bit E. Is that okay? It becomes one input to the second half adder. The other half adder is coming from G, and G is a carry coming from the previous adder. Is that okay so far? Okay. E plus G has a sum, has a result. That becomes the output, the result becomes bit H. Now the most important part is this guy has a carry bit, this guy has a carry bit. But when you look at how we formulate the equation of K, we know what to do with it. Because this carry and this carry, they need to be ORed. I'm just doing a part of the homework assignment here. That eventually becomes K.
Where F go?
Hmm?
Where B and D, where the F go? Should be F.
F becomes J.
Yeah, but just before that, shouldn't F go to?
Because F is on this column here. So you can kind of imagine this side, you have B and D, and that becomes F, and F just goes straight to J here, and the carry of this half adder becomes G. Yep.
AC don't have carry, is that right?
Sorry?
We only have here, which is the anchor E, F, and G, O, G, 0. But for A, B, and C, we don't have carry there.
Say it again.
The first set, A, B, plus C, D, we don't have carry.
What if it doesn't have a carry?
Yeah.
And K is 0.
So we also need to put 0 there.
No, because it's an OR. if this is a 0, if this is false, false, or false is false.
So even we don't have carry, we have to put it.
We always have a carry. The question is that carry a 1 or a 0? Or true, false, right? And since we have a logic gate here, it doesn't matter, right? Because if this is a 0 and this is a 0, then the disjunction of those two is also a 0. We have a carry of 0 as a result. Okay, so now I'm going to use a blue color pen, or red here, and give you an idea of what is a full adder. A full adder is this part. That is a full adder. So a full adder has 2 input bits of the bits that it is adding, 1 input bit from the previous adder, the carry from the previous adder, 1 output, which is the result of this particular bit column, and 1 output, which is the carry going to the next digit column. And that becomes a full adder. And that's why this mechanism is called a half adder, because it is only doing 1/2 of what you need to do of a column of adding.
So a full adder has 4 inputs and 1 output.
It has 3 inputs and 2 outputs. Input, oops, wrong shape. Input, output, and output.
And the H can't be thought of as an input as well for the K.
H, this one?
Like
That's an output.
To get K though, isn't it an input?
That's an output.
Oh, okay.
And so when we keep saying, go ahead.
Say again?
Do we need?
Okay, we have. I'm detecting collision. Okay.
I'll ask. So
Okay, go
that
ahead.
C that we have, those are not C, those are just carries that are going into our OR gate.
Yes.
Yes, these two are outputs from the individual half adders.
So that's what I'm saying, but like, so just for reference with the letters,
Right.
we can just, it's just the carry of its inputs.
In that picture, these wires have no particular label.
Okay, that's what I'm saying, but since we go up there for the initial half adders,
Right.
that C is just the carry of the
Of a
inputs.
half adder.
Yes. So it's just the carry of the top one's the carry of A and C, which is like the top input to the OR. Then the bottom one is the carry from E and G.
Correct. Yes. So when you look at the individual half adder, this is an input pin, that's an input pin, this is an output pin, this is an output pin. So this is what you need to do is to first define what is a half adder as a component, turn it into a component, and use a half adder to make a full adder. Once you have a full adder, turn that into a component, and then use that to make a 4-bit by 4-bit adder, which is really just slapping things together and drawing wires. Yeah. Have her first, and then you next. Go
My
ahead.
question is, if F and 0 we have a carry, are we going to have a 3?
F plus 0 cannot have a carry,
F and 0 cannot have why?
because anything plus 0 is just that thing cannot generate a carry
So if
of 1.
I mean, if we make the first one B and C, if the 0 we put a lot later, that we can also be 1 and 1. So if the F is 1 and the G maybe it's not.
F can be a 1, but 1 plus 0 can only be 1. And that's why F and J are really the same thing.
Yeah, I'm going to use the first example B and D.
Okay?
Yeah, is that if both are 1, so we carry it is 1.
Yes.
If we have carry account, we do here.
Then this becomes 1, right? Because the half adder, D is 1, the carry is a 1. That 1 becomes a part of the input into the full adder of the next digit.
But G is another.
G
That
is,
is the,
it becomes G, right? This wire is actually G. We label G.
but the second one is E and G plus the carry. Is that right? We have to calculate the carry.
E is the partial result coming from here.
Yeah. G is there a lot of.
G is coming from here.
G is coming from there.
G is the carry from the previous adder.
But we use the plus. G is 0.
Okay, so you might need to spend some time to look at this.
Let's
And
put a number there. For example, the E is 1, F is 1, and we use the 0. We use 1 instead of 1, and G use 1 instead of G. So which is so we have 4 1 here. What are we doing?
Can't have four.
cannot have 4 ones.
It's impossible.
It is impossible. Exactly.
Because if B and D are 1, F is going to be 0. And the carry, I guess, you look at the second column actually. If A and C are 1s, E is going to be 0. And if there's a carry of 1 for G, that's going to be 1. So you can't have E and G can't be like.
No, E and G can. Okay. I think I know exactly. Yes, I know exactly what you want to say. You're basically saying A, C, E, and G cannot all be 1s. At least one of those has to be a 0.
Yeah.
Yep, and that is true.
If A is 0, C is 1, F E is 1.
If A is a 0, C is a 1, then it's not going to contribute a carry of 1 either.
Just work out some examples. You'll figure it out.
I'm okay.
Yeah.
Just build a truth table.
Yeah, you will have to figure it out. Okay, that's part of your responsibility.
You brought it from the world.
Yep,
If you were to add a third column, would you just add another full adder?
that's correct. Yep. So if you want to add another, if you want to have a 3-bit by 3-bit adder, I'm just going to draw the picture. I'm not going to use the equation, because once you know the construct of a full adder, you just put on another full adder here. It takes the input, it takes the carry out from the previous digit as carry in. It takes the 2 bits as the input, so that forms the 3 input pins into a full adder. The output is coming here, and then it has its own carry output to potentially the 4th column. So that's why when you work on this homework assignment, I don't want you guys to specify gates the whole time, because this whole thing is one single functional unit. It has 3 inputs, 2 outputs, and this is how you stack them. And once you know how to stack them, making a 16-bit adder is really just a matter of slapping those things, like 16 times.
But also,
Yeah. Oh.
I might be misunderstanding something, but is to make a full adder then, don't you technically need 3 half adders because we have the 3?
We have 2 full adders and 1 OR gate.
But the half adder over here contributing to the G,
Yeah.
its carry is a.
But it is not a part of this full adder. This is really the first digit, the least significant digit, is a special case because the carry, it has no carry from a previous digit.
That's what that
It is
is.
already the least significant digit. So it's kind of like a special case because this carry is automatically the carry to the next digit already, because when you look at the equation, F is going to be added to a 0, which guarantees not to have a carry of 1. So the only possibility of having a carry of 1 is B plus D, and that is already going in to the carry in of the next full adder.
So it's sort of particular to our example.
Correct. Yep. Yep.
Just a quick question. So within the red box, it's
Yeah.
called a half adder. As a
No, the
whole.
red box is a full
It's
adder.
a full adder
Right.
consisting of 2 half adders and
Yep.
then
And OR gate. Yep.
Okay.
Yep.
So when you say a 16-bit adder, do
Yep.
you mean, or a 4x4 adder, do you mean 4 4-bit numbers to be added together, or
Yes. You're adding
2
two-
16-bit?
No, it means you're adding 2 4-bit numbers together,
Okay.
which basically means you just slap 1 more here and you're done.
So 2 full
So, yeah.
4-bit numbers.
Right.
Okay.
So yeah,
Yeah.
so
So this is what your homework assignment should look like. Is you have one kind of like single half adder all by itself, because it's a 0 here. Alternatively, you can turn this into a full adder too, except the input becomes just a constant of 0. You can specify a constant of 0. in the schematic, which will just be wasting some gates, but you know, it's okay too. Yep.
What do we do with the last carry?
Ah, this carry here, you just leave it dangling. It has its own little output pin, and we just leave it there. Yeah. It has a significance because this particular carry, which has no place to store as a part of the sum, is still significant for multiple purposes. But you can just leave it here and just stick a pin to it, so that way, you know, it is represented as a part of the output, but it is not a part of the sum of the adder. All right.
Roll.
Oh, thank you. Today is kind of important because I'm going to take roll, especially of people who are trying to add to the class. So people who have been coming here since the first class and on the wait list, or you know, have your name added after the wait list, I'll give you a permission number today at the end of the lecture. So I'll start with you. And be sure to initial your name on the roll sheet here, because I really go by the roll sheet to see whether people are here or not. And from the empty seats, you can kind of see that there are fewer people today than last Tuesday.
Yeah. Let's say, yeah. After this one,
Okay, so are there any other questions about how to make a full adder? How to make a half adder, and then out of a half adder, use 2 of those and an OR gate to make a full adder. And using full adders, you can just keep slapping more and more full adders and make your n bit adder. You just have to do it n times. Yep.
So 1 full adder is 1 bit, right?
1 full adder is responsible to add 1 bit. Yes. So it will take 1 bit from the first number. It will take 1 bit from the second number. It will take the carry output of a previous digit, and it will output the actual sum of those 2 bits, and it will have an output of a carry to the next digit. And that's why it is stackable. Sorry?
Is that output only 1 bit, right? It's not.
The output is only 1 bit. Yes. But it has another output, which is, well, quote unquote output, which is the carry to the next digit. And that's how it becomes stackable. It's kind of like Lego pieces. So you got to have the shapes and all the pegs, done correctly, so it becomes stackable. All right. Are there any questions about this? No questions? All right, let's move on to the next slide in Moodle. Okay. And you guys will be... Okay, see, this is our next slide. What does it say? Half adding and full adding. Do you guys want me to go through that again?
Yeah.
there's YouTube.
Okay, so let's take a quick look. It has basically all the things that I just talked about. It talks about what a. Okay, I'm just gonna skip all the way to here. This is the truth table. Instead of using B and D, I'm using X and Y as input pins. R is the result, which is the sum, and carry is the output of the carry. So this is the truth table of a half adder. Instead of using exclusive OR, I'm using this equation, which represents exactly the same thing. Okay, this is just another way to say that it is X and not Y, or not X and Y. Because when you do a prime, it means the negation of whatever is before that. Multiplication is conjunction, and addition is disjunction. So there are multiple ways to write the gate expressions, and people do it this way because it is not always the case that they can have a keyboard to type in the circle with a plus or the conjunction or the disjunction symbols. So sometimes they use this particular representation.
And you said that's X and not Y, or not X and Y.
It is X and not Y, or not X and Y. Yep. And the conjunction, the carry of X plus Y is just the conjunction of X and Y. And in this representation, it's using the multiplication. It's borrowing multiplication to mean conjunction in logic expressions. Next slide talks about a full adder. So the full adder is just basically, stacking up. So I'll leave it up to you guys to read the rest of this one. It's really just generalizing stuff. Yep.
But upside down is for all elements.
Yep. Which
So for
means,
all I-
which means this is just an easy way for me to express with an n-bit adder. This is how you formulate the equations. Yeah, for all I being inclusively in a to n minus 1, sum of I, or the sum bit of position I, is the result of adding the result of xy, which are the input bits, and the carry of the previous bit. Which is exactly what we drew here.
Yeah.
Exactly. Except that's more of a mathematical, way to express it. It's the same thing basically. Now, if you are going to, there's one problem with this approach, okay? And you can probably see that if I slap like 64 of these things, 64 full adders, I end up with a 64-bit adder, right?
Yeah.
But there's one problem with that. How long would it take to finish adding two 64-bit numbers?
What?
It will be 64 times the amount of time to finish one bit adder, right? Because it has to wait until, because each one depends on the availability or the validity of the carry bit from the previous one. Now every logic gate is represented or is implemented by transistors, right? You still remember the transistor picture? We have two transistors on the top that are in parallel. Okay. Actually, these are p-channel Mosfets, so the bar goes on the other side. So we have two p-channel Mosfets here. They're in parallel. This is the output, and then we have two n-channel Mosfets in series down here, right? This pin and one of these pins hook up together. This pin and this pin hook up together. This is one input. This is one input. This is my output. This hooks up to VCC, and this hooks up to ground. Okay. Now, I just drew a really poorly drawn picture here. But the point that I want to make is when there's a voltage change at the gate, okay? Let's say there's a voltage change with this pin here, okay? So there's a voltage change. It will go to this pin, and it will go to this pin here. It will take time, okay? It will take time when there's a voltage change here. It will take time in order to turn on or turn off this transistor. It will also take time to turn on or turn off this transistor. That amount of time depends on the area of the junction, which basically forms a small capacitor. So you have to charge or discharge the capacitor in order to turn on or turn off a transistor. So there's a delay. Is that okay? Yep.
Should we know the function of those structures?
Sorry?
Should we know the function of those structures? I don't know. The L.
You're talking about like all those symbols in this schematics.
Yeah, yeah.
This one?
Yeah, like
So,
you know.
the function of those.
The function of
Like
those?
what they do.
Like how that you said that was a MOSFET,
How
so
they
you had to
operate.
change the symbol.
How they
Yeah.
operate? These two are, okay, these two are n-channel MOSFETs.
Like, should we know that?
No.
Oh.
Well, but I did show you a picture of this
You-
earlier.
And
Yep.
that's how it worked and everything.
And these two are p-channel MOSFETs. Okay. I kind of briefly described, this one turns on when the input voltage is low. This one turns on when the input voltage is high.
Yeah, so what I was asking is, should we know that?
I think you should know, when you read my text, you should understand that part, because, it really is helpful to understand, at the physical level, at the lowest, well, almost lowest physical level, how do we implement gates? So I think, it's kind of, well, to me, it's kind of fun to understand that part. I'm not going to ask you any questions about that because this class is not about how to design logic gates using transistors, but just understanding you can use 4 transistors to implement a NAND 2 gate. To me, that is interesting.
Yeah, I like that.
Yeah, yeah. But the most important part of this discussion is this is a NAND gate, but from the time this signal changes to the time this becomes the actual result of the input, there's a propagational delay. We call it a propagational delay because the transistors take time to charge or discharge and change state.
So you're saying that that MOSFET's charging up, and then the switch will close, and that will discharge it to where it's supposed to go. Is that what you're saying?
It will change the state of
Okay.
the actual output.
Okay.
Yep. It's kind of like like a physical switch. If I were to tell someone to turn off the switch or to turn on the switch, there's a delay. After I say I finish my sentence, to the time when the lights are actually off or on. Okay. So there's a propagational delay. Same thing over here. Okay. So this is the propagational delay of one single gate. When you're talking about a half adder, it has more gates than more transistors in that. So there's a propagational delay integral to a half adder. When you look at a full adder, okay, I cannot finish this calculation until this full adder, a half adder, and this half adder are both done. Does that make sense? Okay, so I have some additional propagational delay because of this. Now, when you stack up these full adders, each one depends on the previous one because the carry bit comes from the previous one. So now your propagational delay is just proportional to the number of bits of your adder. Yep.
So I think I'm just mushing out coding with this stuff. But so the OR gate it's not working like the OR operator where
It is an OR operator.
But so how, like in C, once basically like how we, things called like short circuiting. So once we get like for OR, once the
But in this case, you cannot short circuit
okay, that's what I'm asking. Like,
because the availability of these 2 carry bits would not be at the same time. This one is going to be done just like that because this one does not depend on anything else. It only depends on the 2 bits of the numbers that serve as the input. This guy, on the other hand, depends on the input carry, and that can have a long delay because it depends on how many bits are before this particular full adder. But until this guy is done, the output of this OR gate is unreliable because it's not the actual finished product.
oh, but there will be an output, but it's not reliable.
Exactly. There's always an output somewhere, but it's not the actual answer of the 2 numbers that you're trying to add.
Okay, and
So you have to wait a long period of time so that everything can kind of ripple through, and so you have to allow that much time in order for everything, the output and the last carry, to become the actual answer that you need.
okay, so last part. So say from the processor's point of view, it's doing the addition, it's doing this column, so least significant hypothetically. The timing for that full adder, which would control the next column, it's like the powers that the source that's giving it to like start whatever the gate's going. That's not going to go until that carry bit comes in, right? Until like it
That
gets
is correct. Yep. So this is also called the carry ripple, because when you look at it, the carry bit from the least significant digit going through the second bit, going through the third bit, and so on. You can actually kind of envision how this bit is going to change its state as it goes along to the more significant digits.
I guess the last one.
Yep.
Then since we just said that OR gate will always have an output, what prevents that full adder from just starting up since it's technically getting what it thinks
Oh, it will
wants?
always give you an output. Okay, the last adder here. So let's imagine this is like a 64-bit adder, right?
Yeah.
So this is the bit 63, which is the last bit.
Yeah.
Okay. The carry output here is always going to have a state, 0 or 1. Okay, it always has 1. The question is that the actual answer? Until you leave enough time for this guy to settle first, and then the output of this makes this guy settle, the output of this makes this guy settle, and so on, until you leave enough time for all of that stuff to propagate all the way to the most significant digit. The output of the most significant digit and also the sum of the most significant bit is unreliable. They will basically keep changing state because it's using partial answers from the previous gates.
Okay, so the only so it's just basically some time function from all the stuff you're talking about.
Right.
The propagation, and that's how you build a circuit.
Imagine this: instead of having a full adder, I give you guys, the truth table of a full adder. Okay, a full adder, has its own truth table, 3 input and 2 outputs, right? So I will give, each person in this class a truth table, okay? And I will give the entire class the 2 numbers that I'm adding, okay? But each person can only rely on the person next to you for the carry bit of the prior digit. So even though all of you know instantly, okay, I am responsible for bit 23, okay, of these 2 numbers, and you can come up with the answer, this one, right away. You can come up with this answer right away. But you're going to sit there and do nothing because you have to wait until your next neighbor to give you what is the carry bit from the less significant digit. Now, this class does not even have 64 students. But if you kind of imagine, we kind of daisy chain everything like this, using students in this class, it's going to take a long time before the 64-bit number is done. And it's the same way with logic gates. Which is actually very slow. So this is not how Intel actually does its adder. It actually uses another way to speed it up.
How would it know how does it determine the time needed in order to say it's safe to use that answer?
Experimentally, empirically, they would use, so what Intel or AMD would do is they would characterize their, transistors, and just basically, they would try to change the clock speed until, they get past the reliable point,
Okay, so
and then they back up a little bit. Yeah, that's actually how they grade chips. In other words, all the chips, I don't know whether they still do it or not, but in the past, you can buy chips that are rated at 2 gigahertz. Some are rated at 2.2 gigahertz, some are rated at 2.4 gigahertz, and so on, right? And that's they may all come from exactly the same die. It's just that when they go through the characterization process, some would characterize to work reliably at a certain frequency, and some will work at a lower frequency. It's still reliable, but it cannot go all the way up to, let's say, 2.4 gigahertz. So Intel, instead of just tossing it and say, oh, this is kind of defective because it doesn't operate at what we want it to work on, Intel would still be selling it to you at a lower price and say, this is a good chip. It just needs a slower clock.
Yeah. Great 2.3 chip.
Yep. And it's done a lot, with semiconductor. After manufacturing, after you actually get the chip or the die, they would then characterize and sell the chip according to the grade that is characterized at. All right, explicit bits, is exactly what we're doing here. In other words, when you express the calculation of a multi-bit adder, the carry from one digit to the next digit is always explicitly, represented as a wire in this case. Okay. The next slide talks about what if we don't do that? Okay, what if we want to speed up the calculations as much as possible? So you don't have to follow the math. It's just really a mouthful to say those expressions. This is the carry bit out of the first column. This is the carry bit coming out of the second column. This is the definition. But instead of going by the definition, I can expand the R function, which is just the result, and the carry function, which is also a logical expression. So by expanding the expressions, I end up eventually with this expression here. So when you look at this expression, calculate the carry bit out of the second column pretty quickly. There's not as much propagational delay because I can just look at the input bits and come up with the carry output of the second least significant bit and right away. But you can also see the expression is a little bit more complicated, okay? Because it doesn't really, it's not just the R and the C, okay? It is now a little bit more involved. What if I do it to the next bit? If I do it to the next bit, this is the definition, okay? This is the definition of the carry bit, the carry out of bit 2, okay, the bit 2 column, okay, that's the definition of it. But if I use C1, if I use the closed form of C1, which is this expression over here, and I expand R, expand C, which are basically functions with 2 input and 1 output, then I have a much longer and complicated expression like this one. Now this one can probably be simplified a little bit more, okay, but it will still be a pretty long and complicated expression, okay? But the nice thing of doing it this way is the carry bit out of the second least significant column can now be calculated by just looking at the least significant 3 input bits. And I don't have the propagational delay problem anymore. Does everybody understand the rationale of doing it this way? Okay.
But you'll need more inputs. You'll need more inputs then?
Yes, each carry bit will require more input. So when you work on C3, it will require 8 inputs. In other words, it will take the least significant 4 bits of both numbers that you're adding. But it will go through a whole bunch of disjunction and conjunction in order to come up with the carry bit pretty much right away. So it doesn't have the propagational delay that we have with the traditional design of using full adders anymore. So when you do it this way, you're not stacking up full adders anymore. You're basically using complicated equations all the way through in order to speed up your adder.
Will it be pretty much right away by the 63-bit too?
It's not like right away because it will still involve more AND gates and NOT gates, but it will be much faster than relying on the carry bit to propagate. But you can also see the problem of this one is it does get a whole lot more complicated. This is just bit 2. What about bit 63? Yep. And that's why this is not done by hand. If you work for Intel and you ask the guy who designed the processor or the adder part of the 64-bit processor, it's not done by hand at all. It is done by a program. The program will automatically give you the equation, and it will go through an automated optimizer to optimize the equation to use the least number of gates and do it as quickly as possible.
How can we define how many bits we need? How can we find that?
Well, it depends on how fast you want to add and what are the most common width of integers that you want to add.
So it's than 1 already added, or how fast we just predict the numbers really fast?
Well, the current generation of processors are 64-bit processors, right? So that means you want to be able to add 2 64-bit integers in one clock cycle. And doing it this way, you can do it in 1 clock cycle. And that's really kind of fast. I mean, if you think about modern processors, they are really truly a marvel of technology and engineering. And this is just the carry. What about the sum, right? So the sum is nastier. This is no surprise, right? The sum of bit 0, hey, we know how to do that one. Exclusive OR is like that. Okay, cool, we know how to do that. This is the sum of bit 1. Now the sum of bit 1 in this picture is H, okay? So we know how to come up with that one too. It is the result of the result of adding the 2 bit ones from the number itself, and the carry from the less significant bit or the least significant bit in this case. Now, if I expand all the terms and the equations and the functions, I end up with this. And that's just bit 1. So if you think about the complexity of bit 1, and then you think about the complexity of bit 63 of a 64-bit adder, that's going to be quite a bit of an equation.
Yeah.
I would not want to work on it. Okay? But this is the approach to make adders faster. Yep.
Just like, if the knot in between the 2 groups or pieces of, do you read that as, so the first one is essentially exclusive or highlighted. Then
this knot applies to this whole thing.
oh,
Yeah. And this knot applies to this whole thing. So you can see that it's actually, a little bit, it's a bit complicated. But these things can be generated automatically, because once we know the pattern, we can actually write programs to come up with these equations, not a problem. And that's what Intel does. So when you look at the adder on the actual silicon die, it's not like a block of Legos. It's all clean and the same shape, and it's just piled up like this. The adder, when you look at the actual transistors and how the lines are routed, is a big mess. It is a big mess because they need to do it as quickly as possible. If you do it using carry ripple, this way, it's going to be your process is going to be a whole lot slower, because every time you add 1 to a 64-bit number, this end will have to twiddle its thumb and wait and wait and wait until all of the previous full adders have settled down. But doing it this way is a whole lot faster. Yep.
If the 64-bit processor is adding 2 3-bit numbers and has a bunch of leading zeros, will it add the leading zeros or carries the zero? Okay.
Like the full adder does not really care, because there are no special hardware for special numbers. So when we talk about an adder, a 64-bit by 64-bit adder, it is designed to handle general purpose 64-bit by 64-bit addition.
Okay. And also, so if your code has leading zeros in it, the compiler itself is gonna get rid of those. So isn't it only gonna it's gonna get
it doesn't really matter to the processor, because to the processor, it's all the same. Yeah, it's going to exercise the same circuitry regardless of whether you're adding 2 8-bit numbers, 2 16-bit numbers or not. It's all going to go through the same unit to do the calculation. Yeah, because it would cost Intel more silicon to specialize and say, oh, you know what, use this for 8-bit addition, use that for 16-bit addition, use this for 32-bit, and use that one for 64-bit. It would have costed Intel more real estate on the silicon die than just say, okay, just use the 64-bit adder for everything.
So, and I think probably stepping ahead, but so I think kind of looking ahead. So when we're going to add up numbers, I'm gonna use the word you haven't brought, but like register. So we'll have to do we have to, as a programmer in assembly, do we have to make consideration for the fact that
no. You do have to specify, how many bits you're adding or how many bits you're subtracting or comparing, because comparing a 32-bit number is different from comparing an 8-bit number.
Yeah.
Because it depends on how much stuff you're getting from memory and use it for comparing.
Yeah.
But the actual mechanism for the comparison is the same mechanism. It's just that when you do an 8-bit comparison, it will fill up all the more significant bits with zeros before it goes through that circuitry.
Yeah, I think that's what I was trying. Because since we said memories always got some value in it,
Yep.
when we want to go do that, we have to account for the fact that
That is correct.
this area may not have.
In fact, knowing the actual width of what you need when you're writing programs in assembly language is really is of great importance when you're writing programs, because if you use the wrong width, it's not going to do the calculation correctly, or it won't do the correct calculation in all cases. it will do it correctly in some cases, but not all cases. All right, so that is it. Optimization of a full adder for 2 bits. I'm not gonna talk too much about this one. It's a well-known technique of optimizing the use of gates when you're designing the implementation of some output bits. So I'm not gonna spend too much time on this one. You're not gonna get any questions about the optimization technique. If you're going into the computer engineering or electrical engineering program, don't worry, you will see it again. You will see this again, and it will be more complicated, way more complicated as your homework assignment. But if you're on computer science, you probably won't see it much more. Okay, maybe this is the last time you'll see it. Huh? Well, sounds cool. If you know more, it will only give you more ability, later on, transition to go from software to hardware, to make the transition easy. So we are running out of time today. Okay, so the lecture ends now. You do have your homework assignment to implement a 4-bit by 4-bit full adder using just half adders and full adders. In the last time today, I'm going to talk about GDB and the 2 insane running programs that I just, that we saw earlier. So we'll talk about that, during the lab time. All right. If you are trying to add to this class, please come here, and I will give you a permission once I verify that you are actually on the list. So. All right. And you're
Alex Gorski.
Okay, just kind of punch your name. All right. So you might want to do it as quickly as possible, okay? Because I don't know when you need my signature. So do it now, so you don't need my signature.
Sure. Thank you. One more time.
Sure. Yep. All right. There you go.
Hey, yeah, right there at the bottom.
Yep. Yep. There you go.
Thank you.
Right there. Calvin. All right. There you go.
Right there, below.
Which one?
Below top, right here.
Okay. All right. There you go.
I'm down there, so I wait till the other guys.
No. That's fine. We got enough. Yep. All right. There you go.
Down.
Okay. There you go. All right. There you go.
You're recording the lab, right?
In fact, it's still. Oh, yes, I'm
You're
going to
over
record it. Yep.
Okay.
Okay. Actually, I need to turn off the recording now because otherwise it will just go like.